Hello, welcome back to Compressible Flow. I'm Professor Steve Miller. Today we'll be talking about Rayleigh flow and Fanno flow. In particular, we'll look at particular examples and then, of course, some subtleties if the flows are mixed. We'll then look at how the compressible aerodynamics calculator and particular tables are used to solve particular problems. Let's get started today. I like to start with a quote personally. Here's today's quote. It's read by none other than, of course, von Neumann, which we discussed his history previously. And in response to a student who said, I'm afraid I don't understand the method of characteristics, Dr. von Neumann said, "Young man, in mathematics you don't understand things, you just get used to them." Perhaps that's how you felt after we introduced the method of characteristics in a previous module. Nonetheless, let's get to some mathematics which are very much understandable because they're with the simple nonlinear algebraic equations governing Rayleigh flow and Fanno flow. Let's start with a Rayleigh flow example. Here, air enters a constant area duct at M1 equals 0.20, Mach number 2.2, static pressure of an atmosphere, P1, and static temperature T1 of 273 Kelvin. And inside the duct, we find a particular heat transfer rate, total, that is, on a per kilogram basis of 1 times 10 to the 6 joules per kilogram. That's a millijoule per kilogram. We are asked to find what happens at state 2, the downstream location, station 2. And we're asked to find M2, P2, TT, rho 2, the total temperature at 2, and the total pressure at 2. Let's try out the Rayleigh problem. And I think you'll find that this is the most straightforward marching problem for Rayleigh flow there is. Let's look over the solution. First of all, at state 1, we can find the conditions, all the conditions based on the given information of Mach number, pressure, and temperature. That is, at Mach 0.2, using the isentropic equations at station 1 only, we can find the ratios of total temperature to static temperature and total pressure to static pressure at Mach 0.2, which are 1.008 and 1.028 respectively. Therefore, since we know T1 and P1 given in the problem at Mach 0.2, we can find the total temperature and total pressure respectively by multiplying through. They are, respectively, T01, the total temperature at state 1 of 275.2 Kelvin, and a total pressure 1.028 P1, which is, of course, 1.028 atmospheres. Notice the total conditions, of course, are greater than the static conditions, respectively, of 273 Kelvin and an atmosphere. We also know C sub P, which we can calculate from gamma R. So we do 1.4 times 287 for air divided by 0.4, which is 1.4 minus 1. Will be 1005 joules per kilogram Kelvin, which will be essential for the problem. Or you could just look up CP if you desire. Now we can use the thermodynamic first law to march downstream. We know the heat transfer, which is Q. We know C sub P, and we know that from state 1 to 2, we have a delta T naught according to the first law, which we talked about a few classes ago, and you should know by heart from thermodynamic theory. So we know Q, and we know T naught 1 from this calculation right here, 275.2, and therefore we can solve for, of course, T naught 2 right here. T naught 2 will be Q over C sub P plus T01 from, of course, the algebraic relation. Divide both sides by Q, or C sub P, and of course add T01. We now have closed form solution for T02, and we know all the values on the first term on the right-hand side. Filling these in, you'll find that T02 is 1,270 Kelvin. Notice the initial total temperature is 275. Since we added heat into the system, it makes sense that, because it's a Rayleigh flow, and the point of the heat transfer is to raise the total temperature, that the total temperature went up. If the total temperature didn't go up because of increasing Q, you know you made a mistake in your calculation. So let us continue. Now, using the Rayleigh table at Mach 0.2, we can evaluate all the Rayleigh equations through a table lookup. Alternatively, you could put in M for all the Rayleigh equations and find all the static and total values, thermodynamic, with respect to the corresponding reference values. For example, for the T over T sup star with Mach number and gamma Rayleigh equation, you'll find a value of 0.2066. You can also do this, of course, with the Rayleigh flow table lookup. Going across, you should find these values. Now's a good time to try it out on your own by evaluating the equations with your calculator or using the tables. I prefer you try both approaches to become fluent. You'll find, again, ratios of 0.0266 for temperatures. Pressures will have a value of 2.273. Total pressures will be 1.235, and total temperatures will be 0.01736. Remember, the reference or critical value here is the value of temperature, pressure, and total temperature at the critical condition of Mach equals 1 for Rayleigh flow. This is different than the critical condition from isentropic flow. It's a critical Rayleigh condition, m equals 1. Now notice we find the ratio T01 over T naught sup star equals 0.1736. But we really want to, of course, find the ratio of TO2 over T naught sup star. We can write TO2 over T naught sup star as TO2 over T naught sup star times T over 1 divided by TO1. We can then move TO1 in the denominator to the left and T naught sup star to the right, and we find this particular fraction. You'll note that we already know TO2 divided by TO1 from the heat transfer rate in the first law of thermodynamics, and indeed we already know TO1 over T sup star from the Rayleigh flow lookup right here. Let's fill in these values from the previous slide and this slide, and you'll get TO2 over T naught sup star of 0.8013. We can then look up this number and look at, once again, the Rayleigh flow equation for Mach number with T naught over T naught sup star. Indeed, you'll find through that equation and solution for Mach number, or a table lookup, M2 of 0.58. So you'll see from M1.2, a heat transfer rate, positive, will accelerate our flow, which makes sense according to Rayleigh theory. M2 will be 0.58. So we've just solved the most important part of course, the Rayleigh flow problem. We march downstream through, of course, the heat transfer rate relation in the first law of thermodynamics and the Rayleigh flow lookup with the total temperature divided by the total temperature Rayleigh critical ratio. Now we can finish our problem. We know the Mach number at 2, which is 0.58, from, of course, our Rayleigh table. We can then directly look up the relations from the same line on the table or the same set of equations with M2, a ratio of T2 over T sup star 0.8955, rho 2 over rho sup star 1.632, and P naught 2 over P naught sup star of 1.083. And so we're almost done. Once again, we can do fractions to find T2 and P2 respectively, and you'll find that we know T2 over T sup star and T sup star over T1 times T1, which is given in the problem, and multiplying through, you'll get 1,183 Kelvin. You can do the same operation for the pressure, and you'll get 0.718 atm. How did the pressure change in the flow? It went down, of course, with increasing heat transfer in the subsonic flow, which makes physical sense. And indeed, the static temperature went up from, of course, an initial temperature of 273 Kelvin. So we went all the way to 1,183 Kelvin, which makes sense, of course, because we've added a lot of heat to the system. Now, we can also find the total pressures and density through the fractional relation, and the total pressure went down, which makes sense, according to our previous lecture in Rayleigh flow, to 0.902 atm atmospheres. And we can find the density at state 2 because we found P2 and T2 at state 2. You can do these fractional relations or simply use isentropic relations at M2 with the total values to find the static values. It's up to you on how you want to do the problem. This is one preferred method of many people. Let's do another example to solidify these particular concepts. In this case, we'll have an air which will enter a constant area duct at M1 equals 0.5. That's exactly half the transonic condition. We'll have a static temperature, T1 of 300 Kelvin, and a static pressure, P1 of 100 kilopascals. The duct indeed is 10 centimeters in diameter, and it's 100 centimeters long. What is the importance of having a diameter of 10 centimeters and a length of 100 centimeters? Think about this. Now let's let heat be added to the flow at a rate of 90 kilojoules per kilogram. So we're directly given the value of Q. We're asked again to find the Mach number at M2, the static pressure at P2, and the static temperature T2 at the end of the 100 centimeter long particular duct. We'll assume there's no friction and Cp is 1004 joules per kilogram Kelvin. Let's try out the problem. As you can see, this is another Rayleigh problem. Let's look at the solution. First, we need to do and determine the stagnation temperature, because of course for Rayleigh problems, stagnation temperature is the key value, so we can use the first law of thermodynamics. We can find this from the duct entrance because we know T1, the static temperature, is 300 Kelvin, and we know M1, which is 0.5. This is an isentropic formula relating T0 over T with Mach number. You can directly solve this in the table or find it with the isentropic equation. The ratio for Mach 1 equals 0.5 will be T1 over T0 of 0.9524. And then we can directly solve, just like we did in the previous problem, a value and find TO1 equals 215 Kelvin. We now need to march downstream and find TO2. Well, of course, we know the value of TO1, so we'll be able to do this momentarily. Now we can enter the Rayleigh flow table or calculate a Mach 0.5, and we'll obtain the other normalized properties. We can find TO1 over T0 sup star, T1 over T sup star, and P1 over P sup star, which of course are found from the Mach number Rayleigh flow equations or the row of the table for M1 equals 0.5 of the Rayleigh flow table. Let's now determine TO2 over T0 sup star using a simple chain rule. We can see that TO2 over T0 sup star is equal to TO2 over T0 sup star times TO1 divided by TO1. We can thus exchange TO1 in the denominator with T0 star, and we find TO2 divided by TO1 times TO1 divided by T0 star. Indeed, we know T01 over T0 sup star, and we know TO2 over TO1 because, of course, we know the heat transfer rate Q into the flow, which is given as 90 joules per kilogram, kilojoules per kilogram, which is equal to, of course, C sub P times delta T naught. Fill in these ratios once we have them, and you'll find a value of 0.889. Great. Now we can take TO2 over T0 sup star, because T0 sup star doesn't change across the problem, and indeed we can look up through a Rayleigh flow relation. We once again enter the Rayleigh flow tables, or calculator, at TO2 over T0 sup star, and you'll find a value, of course, 0.889, which we just mentioned, and at 0.889, from the Rayleigh flow equations, or tables, you'll find the other values in the row, which will be Mach 2 of 0.67, which makes sense because the flow accelerated with additional heat, T2 over T sup star of 0.975, and P2 over P sup star of 1.4738. We can then seek the static temperature and pressures at the pipe exit directly using the fraction cancellation as we showed previously. You can directly write T2 equals T2 over T sup star times T star over T1 times T1, because we know T1, and likewise for pressure. You'll find 370.2 Kelvin and 82.9 kilopascal for T2 and P2 at state 2. We're almost done. Now, the given length of the pipe and diameter, of course, are totally irrelevant for a Rayleigh flow problem. Don't worry about them. We could add in the heat in a very, very short distance or a very, very, very long distance as long as the flow is frictionless and obtain an exact same result. So, of course, the geometry of the flow is irrelevant. The Streamtube area must be constant, however. We would have to account for variation in area Streamtube if we want to solve these equations appropriately. So remember, you can always use isentropic flow equations at any particular point in the flow, because you are basically, figuratively, deaccelerating the flow to the stagnation conditions. This is also just like you would measure with a probe. We could indeed put a probe in a turbulent flow and find a turbulent pressure and a static pressure, with, of course, vary with time. Now, let's look at a particular temperature entropy diagram for this particular problem. Here the TS diagram is shown with temperature on the y-axis and entropy on the x-axis in figure 388 of this particular slide deck. It is very important you be able to sketch and understand the so-called Rayleigh lines or Rayleigh families of solutions in the TS space. We've done this for our particular problem. You can begin by drawing a relative curve that maybe looks like a thumb on a piece of paper. The upper curve, remember, as we explained previously, is the subsonic regime. We started at M1 equals 0.5. And with heat addition, we accelerated our flow to Mach 2 of 0.67. Indeed, we can also write lines of constant pressure of 100 kPa and 82.9 kPa going through those particular families of the solution. We raised our temperature from 300 to 370 Kelvin, and we can trace those across the sheet. We can also find the exact entropy values because, of course, we know the changes in pressures and temperatures, and we have an entropy equation, delta S equation, that goes as, of course, change in pressures over change in temperatures in the first part of this course. Check out your equation sheets if, of course, you forgot this particular formula, or go back and review. Let's make some more notes about the famous Rayleigh-Fanno flows. Remember, in Fanno flows, we can always make the argument that the effect of heat addition is similar to a slowly convergent stream tube. This is all very much true in Rayleigh flow, where short stream tubes with heat addition might cause expansion or displacement of the surfaces of a boundary layer. And so these effects might be accounted for in different ways. In particular flows, like supersonic flows, the Rayleigh flows might act as a diffuser that drives Mach number towards unity. In this particular case, the temperature, the total temperature, and the pressure increase, and of course the velocity decreases towards the end of the duct, where the critical condition occurs. Let's illustrate this momentarily. Now, in a subsonic flow, the Rayleigh duct, of course, acts as a weakly converging nozzle that accelerates the flow towards Mach 1. Heat addition will always cause the total temperature to increase, but the pressure drops as the flow accelerates. This is how we can physically understand this particular flow phenomenon. We might view the combination of the flows like in Figure 389, and there's a whole module on the course where we can combine in single sets of equations the effects of Rayleigh flow and Fanno flow, but it's beyond this particular lecture. Here we can see we might have a heat addition into a pipe in a subsonic flow, initially in this case, where it might choke at a particular critical condition, which we mark with a star. In both cases, the boundary layer thickness grows as we move downstream in the pipe. Let's now try a Fanno flow example, which we have not done yet in this class. Here, air enters a pipe with an inside diameter of 0.15 meters, and it has a length L of 30 meters, which is rather long and thin. At the inlet in state 1 of this particular pipe, we have a Mach number of 0.3, a pressure of an atmosphere, a temperature of 273 Kelvin. So we know the complete state at 1 through isentropic relations. Now we'll assume that the lumped frictional effect, notice the bar, is equal to 0.005, which we could find from a table for the particular flow Reynolds number in pipe. We're asked to find at state 2, M2, P2, T2, and P02. Let's look over my particular solution. First, as I mentioned, we need to characterize the state of the flow at state 1, the entrance to the pipe. We can again use isentropic tables and relations and look up through M1 equals 3 the ratios of total pressure. We find P0 over P1 of 1.064. We could also use the isentropic equation for Mach number and, of course, total pressure to static pressure ratio. Therefore, since we're given P1, and we can find P01, which is the total pressure at state 1. It's 1.064 atm by multiplying through the initial static pressure. Now we're in a Fanno flow problem, so we won't look at the Rayleigh flow tables, we'll look at the Fanno flow tables or the Fanno equations which we previously developed. In this case, look at the table and look down the first column for M1 equals 0.3. Mind you, do not look in the supersonic part of the tables, of course, because you won't find 0.3. In this particular row, which evaluates all the Fanno equations at a particular Mach number, we'll find particular values, which you can also find analytically from the equations, and I encourage you to do for practice, of 4 F bar sup star divided by D, which is our lumped frictional factor, and we'll find a value of 5.299. You'll then find, with the critical conditions of Fanno flow, P1 over P sup star of 3.619, T1 over T sup star of 1.179, and P01 over P star, is 2.035. All from one table lookup. Try it yourself now. Now remember, our length of the pipe was 30 meters. And just like Rayleigh flow, with the first law of thermodynamics, we can do a graphical solution. And we would relate our length of a pipe as the differences of length of the critical lengths from state 1 and 2, just like we relate with critical Rayleigh number for the Rayleigh flow problem. It's the exact same type of equation. So here we have L equals L1 sup star minus L2 sup star from the graphical solution that follows Rayleigh approach pioneered by Dr. Fanno. Now in this case, we need to find L2 sup star. We know L1 sup star, of course, from the Fanno flow table, which is 4FL over D is a value. And we could solve for L, which is the critical length, L1. And we know L, which is given in the problem. Therefore, we can look for L2 sup star. We can solve this. Now, we can take L2 sup star, multiply by 4, divided by the diameter which is given, and multiply by F bar. That's what we do in this operation. We can also find these two values on the right-hand side by multiplying through by 4, F bar, and divided by D, from, of course, this equation right here, which I'm moving with my cursor. Now, we can fill in the values for L1 sup star and L, because these are given from the problem. L is given, that's the actual length, and L1 sup star is the length to choke the pipe. Of course, if the first value on the right-hand side is less than the second, then our flow is already choked and we can't continue the problem. We'll get for F bar L2 sup star over D of 5.2993 minus 4.005 times 30 over 0.15, and we'll get a value of finally 1.2993, which is important. Now, we can take this value 1.2993 and look up in the subsonic part of the Fanno flow table a value and all rows corresponding to 1.2993, or evaluate it through the equations, and we'll find a Mach number at 2. That Mach number at 2 will be 0.475, which is good because, of course, we accelerated the flow through frictional effects because we're in a subsonic regime, so it checks out physically. That's very important. Now, we can now find corresponding static pressure, static temperature, and total pressure relations through the same type of fractional expansions which we did for Rayleigh flow. The static pressure will go as the fractional expansion, P2 over P1 times P sup star over P sup star times P1. Of course, this means that P2 equals P2. Now, we rearrange P sup star in the denominator, and we have P2 over P sup star times P sup star over P1 times P1. And we know each particular term, first, second, and third, on the right-hand side for static pressure. Let's fill them in from our known values now. We have 2.258 times 1 over 3.169 in a single atmosphere, which is our initial condition. And we'll find 13 atmospheres. You can do the same thing for static temperature and total pressure respectively and find 265.8 Kelvin and total pressure is 0.728, which decreased from, of course, the initial total pressure, which makes a lot of sense. So that completes that example. Let's do another one, except this time with the compressible aerodynamics calculator under the Fanno flow section. The example reads, air enters a constant area insulated duct at M1 equals 0.6, P equals 150 kPa, and T equals 300 Kelvin. And so we know the initial condition of our flow. It's insulated, so that means that there's likely very little heat transfer. Yet there's friction. The duct length is 0.45 meters, the diameter of the duct is 0.03 meters, and has a friction coefficient of 0.02. We seek to find Mach number, pressure, and temperature at the duct exit. Now with Fanno flow problems, we always seek to find, say, 4FL over D or FL over D, depending on the frictional tables. So we'll start by determining if the outlet of the duct is choked or not. That is, have we reached a maximum L? We can do this easy with the compressible aerodynamics calculator or the Fanno flow tables. We simply need to find FL sub max, that's the maximum length to choke, or L sup star for state 1. Indeed, at Mach 0.6, we'll find 0.4908. Use the tables by putting gamma 1.4 for perfect gas in the Fanno flow table or calculator, and in the input Mach number, say 0.06, hit calculate, and then the JavaScript in your web browser will run all these particular values. You'll see here's the input value of 0.6, and over here we have 4FL sup star over D is 0.4908. So that's how we found that value, or you can just use the table lookup. You'll note a very different notation in the calculator for 4L over D, and we need to find the actual value for FL over D for the pipe we're looking to analyze. We would put in, of course, using the values we know from the problem, 0.02, which is the frictional coefficient, times 0.45, which is the length of the pipe, and 0.03, which is the diameter. Indeed, we'll find FL over D of 0.3 of the actual problem, not the choked condition, which is denoted as sup star of Fanno flow. So if we compare the actual FL over D with that which is choked for the given problem, we'll find that 0.3 is indeed less than 0.4908, which means that the flow from Fanno flow is not choked for the given actual length of 0.45 meters. This means this particular combination of FL over D is less than FL max over D for the inlet Mach number of 0.6. Let's illustrate this graphically for the Fanno flow problem so that you can understand the graphical solution. Up here we have a particular duct and we're at state 1. The choked condition shown as L sub max or L sup star is from 1 to the sup star. The actual state which we're going to is at 2, which is a distance from 1 to 2 of L. Also note that state 2 also has a corresponding L2 max to choke the flow, which is also the same distance. This is where we're getting the equation of L plus L2 sup star equals L1 sup star. And so you don't need to remember the equation explicitly. You can just simply draw the pipe and state 1 to 2 and the choke condition and draw the links between them, and you'll have the equation involving the 3/4 FL over D ratios. This is also shown in the temperature entropy diagram in the lower right. The x-axis is entropy, the y-axis is temperature. Here we are at state 1 on a family of Fanno solutions. Here's state 2, and here's the choke condition all the way at maximum entropy. The top line is subsonic flow, and the bottom line is supersonic flow. We're of course in a subsonic regime, so we might start at 1. We go from 1 to 2, which is a distance L. To choke the flow from 1, we would go all the way over from L1 max, distance from 1 to the choke condition. And if we were at state 2 or any other state in the flow, we would say go from from state 2 to the choke condition, that'd be L2 max. You can always see that L plus L sub 2 sup star equals L1 sup star, no matter what. So the equation holds. Now let's try and find FL max over D at location 2. We have, of course, our solution, which is derived graphically just like the Rayleigh equations. We can write FL max over D at state 2 equals FL max over D at state 1 minus FL over D, where L is the actual length from 1 to 2. We can then put in the values which we know. We know 0.4908 minus 0.3 from our previous calculations on the right-hand side of this equation. Evaluates to 0.1908. Now let's use the calculator or table lookup. We once again put in 1.4 for the ratio specific heats gamma, and the input we know we're in the subsonic regime, so we'll select subsonic SUB and 4FL sup star over D, and we'll put in 1.908. We then hit the calculate button. Indeed, we get a lot of values out, including all the values of say T2 over T sup star, P2 over P sup star, P naught 2 over P naught sup star, velocity over velocity sup star, and 4FL sup star over D of 1.908, which is just echoing the input value. You also get the entropy increase. And so now we know all the ratios at state 1 and state 2, and we can do our fractional expansions just like we did in the most basic problem example which we previously did. I'll let you do that work yourself to confirm the work. At 2, you'll find a static pressure of 125 kPa and a static temperature of 292 Kelvin. You should go now, look back on your work, and confirm indeed that these values changed with the physical correspondence of Fanno flow, which you should have memorized as physics. Let's look at a particular Fanno flow of this example one more time. We went from Mach 0.6 to Mach 0.71. Indeed, the Mach number increased with friction. And we went down in temperature from 300 to 292 Kelvin. And we increased in entropy. And we drew lines of constant pressure through the TS diagram as dashed lines through state 1, 2, and of course P sup star at locations 1, 2, and the critical Fanno flow location respectively. Simple. Let's look more at this particular example. Let's say we wanted to find the maximum flow rate through an existing subsonic Fanno pipe. Here we have a large plenum. There's a total pressure and temperature within it, and it converges down to a small diameter pipe which goes into a chemical reactor. You might imagine yourself that you're not an aerospace engineer, but a chemical engineer. I'm sorry that things didn't work out well in life for you, that you didn't remain an aerospace engineer. But life isn't perfect for everybody. I suppose there's good things in the world that chemical engineers have done, but not as good as aerospace engineers. Anyway, there's an existing long frictional pipe between the high-pressure gas tank and, of course, the back lot area where the chemical reactor is. It needs gas as a so-called feedstock, and we might find a mass flow rate and keep it constant by choking. We might ask ourselves, what is the maximum mass flow rate through the existing pipe? And for a given storage tank at P0 and T0, located in the plenum, and a given length L between, of course, the storage length and the reactor, we need to find a particular diameter and friction factor F for a maximum mass flow occurring when the exit of the pipe is choked by friction, right here at maximum L. So right away we know that L is going to be equal to L soup star for the particular problem. Let's get started. If the flow is not choked, then we cannot get mass flow rate increasing by dropping the back pressure, just like in the nozzle problem. It's the exact same physics. So choking the flow will not increase the mass flow rate, even though here we'll be choking the flow with frictional effects instead of, say, a converging diverging nozzle. Afterwards, the mass flow rate, of course, will be the same unless we raise the total pressure or lower total temperature or replace the entire pipe, which is rather impractical once it's built. Now, we can find FL over D of the pipe and look that up as FL max over D. This will give us a particular value of M1. Now, for a very short convergence section of the nozzle right here, we can just assume that that part of the flow is isentropic through the nozzle section. We can then get P1 over P0 and T1 over T0 from the isentropic tables to relate the total values to the values at 1, or calculate M1 directly. We would then finally find the mass flow rate at station 1 of the pipe, right here. And note here we set L max to be L soup star by choking the outlet of the pipe at 2. We can then write the mass flow rate, M dot, equals rho AV through the pipe, continuity equation, and we'll replace density with P over RT, the ideal gas law. We'll retain A and write it as A sub 1. And we'll write U, or the velocity at 1, as the Mach number at 1 times the speed of sound at 1, square root of gamma RT1, which is, of course, not unity in this case because 1 is not choked, 2 is choked. Let's fill in some numbers to try and give an example problem. Let's say that we have a 20 centimeter long by 2 centimeter diameter pipe, and the frictional effect is 0.032. It's connected to a reservoir with a total pressure of a megapascal, a total temperature of 500 Kelvin, and the working fluid has gamma of 1.4, ratio of Cp over Cv. We can go through the problem I just illustrated to determine the maximum mass flow in kilograms per second of air through this duct. And we can also look for a range of back pressures where this mass flow rate is indeed realized. We'll then repeat the calculations for the nozzle only with no frictional effects and compare the two. We'll look for these values. Let's look at the solution. The maximum flow rate, remember, occurs when the nozzle exit is choked by friction, which is at state 2 for the case with the pipe, or at state 1 with no pipe. So with the pipe, we might say FL over D of the pipe will be 0.32 because we know FL over D, which is going to be set to FL max over D because it's choked at 2. Let's use the calculator for this problem. You can also use the tables or equations. Indeed, we'll select FL for FL soup star over D for subsonic flow and put in 0.32, which we just found, and hit calculate for gamma 1.4. You'll then see at state 1, we have a Mach number of 0.65. That means the Mach number at 1 is 0.65, which must be obtained by the nozzle for these conditions. You'll also find the other ratios of pressures and temperatures and total pressures and 4FL over D for the particular value there. Now we need to find the particular Mach numbers in the isentropic section to obtain M1 of 0.65 at state 1. So we can do an isentropic relation problem in the nozzle. So given a total pressure of a megapascal and a total temperature of 500 Kelvin, the nozzle will have to deliver a static pressure of 752 kilopascals and 461 Kelvin to the pipe, according to isentropic relations with this divergent section, which is a part of a problem we discussed previously, so I'll leave some of these details to you. We can then plug in these static values into the mass flow rate equation at state 1. We know pressure, temperature, area, Mach 1, and T1. Putting these in, you'll find a mass flow rate at state 1 of the choked pipe flow of 0.5 kilograms per second. Also, of course, the flow will be choked for other ranges of pressures. Of course, because of raising the pressures, it won't matter. The flow is choked and remains choked. And you can't change the mass flow rate by increasing the pressure ratio. Now we can do the problem without the Fanno duct, that is the nozzle alone. And of course, with only a nozzle going to the reactor, the Mach number would be 1 at the nozzle exit. We then can just do a simple isentropic flow equation to find static pressure and static temperature at Mach 1 from the total conditions in the nozzle, which were given in the original problem. A whole range of back pressures will choke that nozzle, as we discussed for the whole isentropic nozzle section of the class. The choking range will be from 0 to 528 kPa at station 1 for choking the nozzle, based on the critical pressure ratio of gamma 1.4, which is of course about 1.89. We can graph these particular solutions. On the x-axis we have a particular back pressure and a total pressure held constant at 1000. For the nozzle only, we can obtain a maximum mass flow rate of 0.57, which can be evaluated with the same mass flow rate equation we developed at state 1 for the Fanno flow nozzle problem. If we add in the duct, we can only maintain a lower mass flow rate, which might be viewed as a loss due to potential mass flow rate, that is, due to the frictional effects in the long duct. And so if you want to have a higher mass flow rate into your chemical reactors, you would of course have to have a shorter duct is preferential. Of course, you would never want to put your bottle field too close to your reactors for safety reasons, and so some length of pipe is required. We can also look at this problem in terms of graphs, where we have in the upper part an inviscid flow connected to a viscous Fanno flow, where we have a total pressure connected to a long pipe with a back pressure. As we lower the back pressure, we can see multiple graphs of the particular flow through the nozzle through the viscous Fanno flow regime. The flow moves from left to right and accelerates and is subsonic through the whole pipe and chokes exactly at the entrance to the chemical reactor right when we find L max. These other cases are, of course, completely subsonic Fanno flow problems that never choke, and they would have to be solved through the normal approach. The nice thing about choking the Fanno flow for outlet flow means that, of course, this calculation is simple, and we only need one FL over D value, because we don't have to do the subtraction between 1 and 2 like we did in the Fanno flow problem, which we just showed in this class. You'll have to try out these problems on your own and follow along in these examples to understand, I think. You can see indeed that all the analysis that we conducted involves really a friction coefficient, which we defined as the lumped or average Fanno flow friction coefficient. And we already presented this equation in a previous class, but I'll put it here just to remind you. Remember, F bar, which is what we're using in the equations, goes as 1 over the length of the pipe times an integral over the length of the frictional effect, which is a function of x dx. So it's just the average property. And this is very often what's shown in a particular Moody chart, which lists frictional values. These are often found on the internet or basic fluid dynamics textbooks, but we won't be looking at these charts. We'll just give you frictional effects because I don't find this to be a worthwhile exercise to understand physics. Usually F is given as a function of Reynolds number, and it's very much relative to the roughness of the pipe. And so these charts and books of charts are very large. It's not very practical. That's why they're found in computer lookup tables in practice in simple systems to design, say, chemical engineering plants or compressible gas pipelines. This always assumes fully developed flows. So in very short pipes, this is actually not a very good estimation of the average frictional effect. So if you have a pipe which is, say, less than 10 diameters long, non-dimensionalized if you will, then of course the Moody charts won't be very useful because you might have a bad estimate of F. That's because the turbulent flow is not yet developed and might be transitional, and therefore you might have higher frictional effects. This is all named after these charts, of course, of Louis Ferry Moody, and he lived from 1880 to 1953, and he's American, which is a nice change from many of the past historical figures, because I'm an American. He was a professor of fluid mechanics and machine design and indeed taught at Princeton University starting in 1930. He's today known best for the Moody charts, and indeed his pictures and portraits are in Princeton today. He drew these diagrams showing the particular pipe flows and calculating frictional factors through the flows. Indeed, today, the American Society of Mechanical Engineers created an award called the Louis F. Moody Award, which still exists today also. There's this nice picture on the right. In this class today, we discussed the famous Fanno and Rayleigh flow examples and showed a few complexities. We went through these examples, but the only way to understand the physics is to try it out on your own, both mathematically deriving the equations and repeating the examples, and trying to think about the mathematical relationship between the equations and, of course, the flows. Thank you very much for your time today. I'm Professor Steve Miller.